The next topic is called infinite series. Before we talk about infinite series, let's recall what we know about infinite sequences. So here's the notation. We have open brackets a index n, close brackets, and when we see this, we know we have the following. And what this is really a function where the input values are the positive integers 1, 2, 3, n, all the way to infinity, and the output values are a1, a2, a3, an, and there are values that go on all the way to infinity. Now let us define what an infinite series is. So an infinite series is simply the sum of the terms in an infinite sequence. Therefore, what we have is the following. So we have the sum of the numbers a index n from n is equal to 1 all the way to infinity. And the question that we ask ourselves is, does an infinite series converge to a finite number? Is it possible to have an infinite sum of numbers that is equal to a finite number? Or do infinite series always diverge? And to answer this question, we have to define the following, which is the nth partial sum of an infinite series. So given an infinite series, the nth partial sum of the series, written capital S index capital N, is equal to the sum running from n is equal to 1 to capital N a index n, and that sum is here. So now if we form the sequence of partial sums, so this infinite sequence here, for all of the different integer values of capital N, and if that sequence converges to the number s, which is a finite number, and we go back to our definition of convergence of a sequence, so the limit as n approaches infinity of s of n, so if that limit is equal to s, then we'll say that the series converges and has the following sum, equals to s. And if that sequence diverges, then our infinite series also diverges. We're now going to look at an example. Let's begin by considering the following series. And let's write out the terms of this series. And let's determine if this series converges or diverges. And to do so, we need to look at the partial sums of the series. And the nth partial sum is given by the following. And the sequence of the partial sums is given by the following. And let's write out a few terms of this sequence to understand whether or not it converges or diverges. So the first term is when capital N is equal to 1. And when capital N is equal to 1 in our series, well, we get the following, which is equal to 1. And now let's look at the second term of the sequence, which is, so now the sum running from n is equal to 1 to 2, and this gives the following. So we have our first partial sum plus the second partial sum, which is minus 1 to the power of 2 plus 1, minus 1 to the power of 3, and this here gives minus 1, so I've got 1 minus 1 is equal to 0. And now let's look at our third partial sum. And in the third partial sum, I have the second partial sum plus minus 1 to the power of 3 plus 1, and this gives minus 1 to the power of 4, which is equal to 1. And what we see now is that our sequence is alternating between 1 and 0. So it goes 1, 0, 1, and it continues just like this. So the next term is going to be 0, the term after that is 1, and this goes on all the way to infinity. And a sequence that alternates like this between two values doesn't converge, and we say that diverges. Therefore, and given that the sequence of the partial sums, capital S index capital N, diverges, we say that the infinite series also diverges. And let's look at another example. So let's consider the following series. And once again, let's determine if this series converges or diverges. So what we need to do is to write the nth partial sum of the series, which is. And once again, we need to determine if the sequence of partial sums converges or diverges. Therefore, we look at the sequence of S index n. And to find the sequence, we're going to begin by simplifying our expression for the partial sums. And the first part in the simplification is rewriting this fraction here as a sum of partial fractions. Therefore, on the denominator we have distinct factors, therefore we get the following. And now we determine the values of a and b. And I begin by finding a by subbing in n is equal to 0. And I find b by subbing in n is equal to minus 1. Therefore, our partial sums can be rewritten as, and we can continue to simplify the partial sums by writing out a few terms of this series. Here's the first term, and the second term, and the third term, and the final term in the series. And what we see now is that there are many things that cancel out in this expression. So the minus 1 over half cancels out with the 1 over 2, the minus 1 over 3 with the 1 over 3, and this minus 1 over 4 cancels out with the next term, which we don't see here, and this term here cancels out with the term that we don't see here. So our partial sum simplifies to, and we write our sequence of partial sums as, and to find if this sequence converges, we take the limit of the nth term as n approaches infinity, which is, and this limit is equal to, so we have 1 minus 0, because as n goes to infinity, well, this term here approaches 1 over infinity, which approaches 0. Therefore, the sequence converges, and we say that the infinite series also converges. And in this case, the value that it converges to is s is equal to 1. Therefore, our infinite series is equal to 1.